This barrel is 0.7747 meters.
So I will be dropping this old cassette tape from this blue barrel.
The ladder is 1.854 meters.
So I will now be dropping this cassette tape from the top of this ladder.
The cassette tape, when it was dropped from the two different heights, had gravitational potential energy. Gravitational potential energy is the potential energy an object has to do something with its surroundings, and this happens due to gravity. To find potential energy of gravity, it is mass times the acceleration of gravity times the height. The mass of this cassette tape was 0.0405398 kilograms. The acceleration of gravity, like always, is 9.8 meters per second squared. And the height for when it was dropped from the barrel was, like I said earlier, 0.7747 meters. And the ladder, like I said earlier, was 1.854 meters. The potential energy of gravity for the barrel, we used all the information, like how I said above, and we got 0.307780746 joules of energy, and that's the gravitational potential energy the object had. For when it was dropped from the ladder, the cassette tape, the potential energy of gravity for it was, with using that information, was 0.736576098 joules. When the cassette tape was dropped from the barrel and the ladder, it had kinetic energy. Kinetic energy is the energy an object has to be propelled into action. The formula for kinetic energy is 1 divided by 2 times mass times velocity squared. Speed squared, sorry. The mass of this cassette tape during the droppings was 0.0405398 kilograms. For when the cassette tape was dropped from the barrel, its speed was 3.15 meters per second. So when plugging all this stuff into the formula, you get the kinetic energy, and also square rooting the speed, you get the kinetic energy of 0.20112818 joules as the kinetic energy of the cassette tape when it was dropped from the barrel, the height of the barrel. When the cassette tape was dropped from the ladder, its kinetic energy, when plugging in everything with the speed of 2.11 meters per second, the kinetic energy was 0.090243666. For both drops, they would have the same free body diagram. In this diagram, the force of gravity is pushing the cassette tape down after it is released from the top of both heights. The force of gravity is pushing it down. Then a normal force, air resistance, is causing resistance for the object because air resistance is going up as the normal force.
So this is an elastic object. When this elastic object is stretched or compressed, it has potential energy. Then let's say if you shoot this object, this elastic object gets kinetic energy like this.
When the hair tie is in its original form, it is 0.039624 meters. When the hair tie is stretched, its length is 0.141224 meters. The hair tie had elastic potential energy. Elastic potential energy is the energy available to a deformed elastic object or spring to return to its original form, or that allows it to return to its original form. To find potential elastic potential energy, it is 1 over 2 times the spring constant times the length between the stretched hair tie, well, in this case, the stretched hair tie, and its original form, squared. So first we would have to find the spring constant, which spring constant is mass times the acceleration of gravity times the deformed length between the stretched hair tie and when it was in its original form. So using the mass of the hair tie, which was 0.0680389 kilograms, times the acceleration of gravity, which is 9.8 meters per second squared, over the deformed lengths, which when it stretched, it was 0.141224 meters minus 0.039624 meters. Doing this math, the spring constant comes out to be 6.562807 joules. Now with the spring constant, elastic potential energy can be found. So multiplying the spring constant by the length between the stretched hair tie and its original form squared, then times 1 over 2, the elastic potential energy comes out to be 0.033872486 joules. In both situations, there was kinetic and potential energy. For potential energy, the cassette tape, when it was dropped from the height of the barrel and the ladder, there was potential. Well, before when I was holding it there was potential energy of the potential energy of the cassette tape being able to drop due to the forces of gravity. In the case of the hair tie, there was potential energy when the hair tie was being stretched. There was kinetic energy in both cases when also. For the cassette tape, it was when it was dropping and it had the ability to be in action. And then for the hair tie, it was when it was getting flinged after stretching. Measure of energy that is transferred when an external force is acting upon an object. So, in this case, an example of work is me pushing this barrel. And during this, I'm pushing my energy into the barrel to make it move. So my work is pushing this barrel. And a part of work is the angle at which it's happening. So there's the vector of the force applied, which is me, my hands, and then there's the vector of displacement, which is the distance it's covering, which is the displacement the object, the barrel is going. The displacement the barrel traveled was 0.8763 meters. The time it took to travel that was 4.88 seconds. The angle between the vector of displacement and the vector of applied force was 117 degrees. With this information, work can be found. To find work, the formula for work is force times the displacement times the cosine of the angle of the vector of displacement and the vector of the force applied. To find the force applied, the mass and acceleration need to be multiplied by each other to get the force. So the mass of the blue barrel, which was being pushed, was 9071.85 grams. And then the acceleration of when it was being pushed was 0.180090164 meters per second squared. Force, so that would make the force be 1633.75094 newtons. Since the force is now found, work can be found. So using the force multiplied by the displacement of 0.87884 times the cosine of the angle of the vector of displacement and the vector of the force applied, which is 117 degrees, work can be found, which is 651.842142 joules. When I was pushing the barrel, a free body diagram can be made. In the free body diagram, the force applied, which is me pushing against the barrel, goes down. And then that's the vector of the force applied. The vector of displacement goes across that way, and then the angle between both of them is 117 degrees. Okay, so power is the next thing I'll be talking about. Power is the rate at which work is done. Power is it is work divided by time. So it would be joules over seconds, which then becomes watts. So the unit for power is watts. So an example of power is be a machine like this KitchenAid, which is used to stir things around, make dough. You make cookie dough, waffle mix, anything, pancake mix. It's old though. So, but so if you turn it, first start turning it on. I'm not sure exactly how many watts are going to it, but a small amount of watts of power are going to this. But when you turn it higher, all the way up to 10, a lot more watts of power are going to the machine to make it stir faster. So the more watts that are going to the machine means more power is being put to it to make it work faster and harder.